Hello, welcome back, students. Let us continue our series on relative velocity. Today, we are looking at relative velocity of inclined vectors. If the vectors are not parallel, if they are not parallel but inclined, these are parallel vectors, right? If they are not parallel and they are inclined, for example, one is moving due north, one is moving due east. When you put these two vectors together, you realize that they will not be parallel. You get something like this, right? So this will be inclined vectors. When you have a situation where one vector is like this and another one is, let's say, like this, when you put this vector and this vector together, you realize that the net vector is going to be inclined, right? You are going to get something like this. Let me clean this top and put it here. So you see where it's going. I'm going to get this. This will be this. This will be this. So you can clearly see that situations like this, the vectors are inclined. When you have such problems, then you can use the triangle of vectors, the parallelogram law, or the resolution method to solve such problems. But I prefer the resolution method because to me, finding the magnitude and the direction becomes so simple. So let's stick to that. I'm going to show you some steps you can use, you can adapt when you want to use the resolution method. So if you want to use the resolution method to solve relative velocity problems, these are some of the steps. First of all, try and get the magnitude and the direction of each vector. Okay, get them separately. And if you are looking for the direction, the next step is that the direction of each vector, you have to take it from the north in clockwise direction to the vector. What do we mean by that? I'm going to show you very soon. Then each vector, you express each vector in a column form. After expressing each vector, let's assume that the vector from the north for a given vector is theta and the magnitude is v. Then how do you express the column vector? It's going to be v sine theta, v cos theta. Okay? So you can be pausing the video and be writing the steps down. We will use the steps to get every problem that we will come across. All right. Then, depending on what the question is asking you to do, write down a relative velocity of a relative velocity expression which the question demands. Velocity of which one relative to which one are you asked to find? Look at it from the question, then you write it down. Then you insert your column vectors you have obtained. You have already obtained your column vectors in step 3. So you insert the column vectors in the relative velocity equation you write here. Just insert them there. So after inserting and simplifying, you will still get a column vector as your answer. So if you have a column vector, for example, like this, then finding the magnitude and the direction becomes so simple. The magnitude will be, of course, this. Then the direction you draw the cardinal point, then you calculate it from the north. Let us pick example. I'm going to use example to explain these steps I have for you. Okay? And you are going to love it. So this is the question. Ship X is steaming due east at 15 kilometers per hour. Ship Y north due south, steaming due south at 20 kilometers per hour. Find the velocity of Y relative to X and its direction. Wonderful question. How do we solve it? So we said as step 1, what do you do? From our steps, we have to find the magnitude and the direction separately. So let's go. Solution. The first one is moving 15 kilometers due east. So how do I draw it? 15 kilometers due east. This is 15 kilometers per. This is for shape X. And that one, the second one is, you can go back to the question and check. For Y, it is 20 kilometers per hour due south, right? Right? Sorry. So, try and then find then the next step is that what? The direction of each vector is found. You find it by taking it from the north in clockwise direction. So what do we do? From there, you can express them as column vector. So let me try and write them separately. So for X, okay, Vx, what is the magnitude? The magnitude is 15 kilometers per hour. The direction, you take it from the north. This is the north in clockwise direction up to the vector line. This is the vector 15. So the angle there is what? 90 degrees, right? 090, or simply 90 degrees. I prefer the 0 here. 0 tells you that it's from the north. For Y, what do you do there? Vy is equal to, this is Y. So you take it from the north in clockwise direction up to the vector. This. What angle is this? 180. So 20 kilometers per hour, 180 degrees. So that is what we have done for, that is the meaning of step 1. Okay? And step 2. Now we are going to express each of them as column vector. And how do we express it? We use this expression. Before you can use this expression, then you have found the angle from the north in clockwise direction. So we will just express each of them as column vector, right? So what do we do? So we say that I advise, what is the question asking us to find? We are asked to find the velocity of Y relative to X, okay? So why don't we write an expression for that? We want the velocity. How do we write velocity of Y relative to X? Velocity of Y relative to X is given by Vy plus the minus of what? Vx. So simply Vy minus Vx. Let's call this equation 1. We are not going to do any simultaneous equation, just for reference purposes. So where are your Vy's and where are your Vx? They are here. So we are going to express them in column form. Well, see this. We are going to express them in column vectors. That's what I was saying. So we write here expressing Vx and Vy as column vectors. How do we express them as column vectors? We can express them from this thing we wrote. When you know the angle from the north, look at this. Very simple. And how did we get this? We got this from the diagram here. I hope you are following. Good. So I will say Vx. How do I get it? Vx, the column form is going to give, the magnitude is 15. So 15 sine 90, 15 cos 90 degrees. Then this one will be what? This one will be 20 sine 180, 20 cos 180. So I'm going to write this nicely on the next page. This one was just a rough work. I'm transferring this one to the next page. So what do we get? We get Vx to be 15 sine 90 degrees, 15 cos 90 degrees. And what do we get for this? This, according to our calculator, sine 90 is 1, so we get 15. Cos 90 is 0, so 0. Okay? Let me call this equation 2. Then y will also give us 20 sine 180. I'm just transferring what I wrote. 20 cos 180. And this gives us 0. Let me check. With our calculator, sine 180 is 0. So we get this 20 sine, then cos 180 is -1. So get -20. Right? Let's call this equation 3. The question wants us to find the magnitude and the direction of the velocity of y relative to x. So look at this. We are going to put 2 and 3 into 1. Then we are there. So putting 2 and 3 into equation 1. So putting 2, 3 into 1. And what do we get? Then yx is equal to what? It's then y minus then x, okay? So, because the question asks us to find then yx. So what is our then y? 0, -20. Minus our then x is what? 15, 0. When you simplify this, what do you get? 0 minus 15 minus 20 minus 0. We end up getting -15, -20. So this is kilometers per hour. But this is not our destination, because we are supposed to, according to the question, we are supposed to find the velocity of y relative to x and its direction. So we need the magnitude and the direction. So what do? Then yx is equal to the square root of, that is what this step is saying. We are here. Now we have gotten this form. You see what we were saying? So we have gotten it to be this. That is what we have gotten to be this. So we are going to find the magnitude. We are here. This way. I hope you are following. Very good. So now let's go. -15 squared plus -20 squared. And when we simplify this, we are going to get 225 plus 400. Okay. So magnitude of Vyx, 225 plus 400 gives us 625. And this gives us 25 kilometers per hour. Now, how do we find the direction? Don't forget that the column vector was what? The column vector, what did we get? We had -15, -20, right? If I'm right. Yes, that is the column vector. So we are going to use this column vector to find the direction. So that is, we are on the final part, the direction. This is where we are. Okay. How do we find the direction? You just draw your cardinal point as usual, or your cardinal point, or your Cartesian plane, or whatever. So look at this. Negative, the first component is the x component. This is a Cartesian plane rather, okay? X component is negative. So if it's x component, this zone, negative x is here. Y, the -20 is y component. And this is negative zone. According to the Cartesian plane, we know that this is positive y, negative y. Is that not it? Positive x, negative x. I hope you remember this. Good. So if I want to use that idea, let me draw it somewhere here just to guide you. So we know of this as this positive y, positive x, negative x. So if I have negative 15, negative 20, we need to look for which zone it will lie. Negative x, 15 is x, y is positive, negative. So it will lie in this region. So just draw any vector. Don't make it too long. So something like this is okay. Then we can make our theta. We can put our theta here or here, but I prefer that we put the theta to the x. Let me call this angle theta. So that if I have a right angle triangle, let me draw a right angle triangle to complete this. Where my negative is my x. So if I have this right angle triangle, where is my y and where is my x? This is my x, so 15, and this will be my y, 20. I won't bring the sign. The sign was also the sign only enabled me to know the region where my angle will lie. So I won't add any negative there. All right. So look at this. There is a right angle triangle. Here is 90. So which trigonometric ratio do I use? This becomes the opposite and this is adjacent. So tan theta 20 over 15. And 20 over 15, according to calculator, what do you get? You get 1.33333333. So what do we get theta to be? The tan inverse. Okay. And what do we get? So theta, tan inverse of 1.33 in degrees is going to give us to 2 decimal places, 3 decimal places, 129 degrees. So that is our angle. We need to conclude properly. Go to the diagram. So if I'm using cardinal point to read this, then this becomes west. West theta degrees what? South. This is west. This is south. So I can read this as what? West theta south, right? Okay. Or if you are taking it from the north, then I'll say that it is going to be the whole of this angle. So there are two ways you can state it. What is this angle? The angle from the north to this. It is 270 minus theta, right? Yes. 270 minus theta. So whichever way you state it is correct. So what do we say? The velocity of y relative to x is 25 kilometers per hour. And the direction is, as I was saying, west theta. What is theta? West 53.129 degrees south. That's all. Or somebody can state it this way. Any way is acceptable. 100% correct. The velocity of y, the velocity of y relative to x is 25 kilometers per hour, and the direction is, as I was saying, you can also take it from the north in clockwise direction. And in that case, it's going to be 270 minus theta. Okay? Depending on the region where it is lying now, is 270 degrees. 270 minus theta. And this is equal to 270 minus 53.129. And this is what? 216.87 degrees. All right, so that answers our nice question. So you can choose to use this one, or the second one, or this one. Any way is acceptable. All right, on this note, I think we can end here on relative velocity of inclined vectors. In our next lesson, I want to solve one more example for you, so that when I solve one more example for you, you can try your hands on some trial examples that will be given to you. All right, I'll be waiting for your comments, and don't forget to subscribe. See you in the next lesson. Thank you. Goodbye.